Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Let's start our class today by reciting prayers and blessing upon Nabi Muhammad sallallahu alaihi wasallam. Bismillahirrahmanirrahim. Rabbi zidni ilman warzuqni fahman. Allahumma salli ala sayyidina Muhammad salatan taj'aluna biha min ahlil ilmi zahiran wa batinan wa tahsyuruna bi'ibadika salihin fi dunyana wa akhrana wa ala alihi wa sahbihi wa barik wa sallim. Okay, we'll continue our class today on the fourth subtopic, high voltage electrical supply. In high voltage electrical supply, there are four main subtopics. The first one is main transmission line network system, followed by the primary distribution network system, and then followed by secondary distribution network system, and finally we will discuss on types of electrical supply users. Okay, the main transmission line network system is connecting the electrical supply source from electrical generation station to the main distribution network system at certain large areas like states, districts, and also big towns. And then the main transmission line network are like to each other to form the national grid system. And then the method used in the transmission line network is the three-phase, three lines, red, yellow, blue system through the main overhead line. And then for primary distribution network system, it will receive electrical supply from main transmission line network system. It is located at a few selected locations in a state. And then the electrical power is delivered to the users through four distribution levels. So we will discuss on the four distribution level. Okay, the first level called Transmission Main Intake TMI or Pencawang Masuk Utama PMU. TMI or PMU is the interconnection point of 132 kV or 275 kV to the distribution network. So this is the example of PMU at Seberang Jaya, Pulau Pinang. So, the standard transmission capacity and voltage transformation provided at the PMU are as follows. So, 132 step down into 33 kV, 132 kV step down into 22 kV, or 132 kV step down into 11 kV. And then the second level is the main distribution substation MDS or Pencawang Pembahagian Utama PPU. So this is the example of MDS or PPU. So main distribution substation is normally applicable to the 33 kV for interconnecting 33 kV networks with the 11 kV networks. So basically, it provides capacity injection into 11 kV network through a standardized transformation of 33 to the 11. We move to the third level. So the third level is the main switching station MSS or Station Switch Utama SSU. So SSU at 33 kV, 22 kV and 11 kV are established to serve the following function. Which is to supply a dedicated bulk consumer and also to provide bulk capacity injection or transfer from PMU or PPU to a load center for further localized distribution. So this is the example of the SSU. And then finally, okay, we go to the fourth level, distribution substation DS or Pencawang Elektrik PE. So distribution substation are capacity injection points from 11 kV, 22 kV and sometimes 33 kV system to the low voltage network, which is 400 volt and 230 volt. So typically capacity rating are 1000 kVA, 750 kVA, 500 kVA and also 300 kVA. Okay, for your information, underground cables are used in the delivery system from level 1 until level 4. So the types of underground cable may be 3C times 300 millimeter squared and etc. as you can read by yourself. And then the block diagram of this system are from the main transmission line, go to the TMI, the transmission main intake, and then go to the second level MDS, main distribution substation, and then go to the third level MSS, which is main switching station, and finally distribute to the distribution station. For secondary distribution network system, it begins whenever the high voltage electrical supply such as 11 kV received at distribution substation is converted to the low voltage electrical supply, for example 400 volt. The method used is the 4 lines, red, yellow, blue and neutral, through the step-down transformer. And then the number of distribution substation is depends on the total load demand VA requested by the user. The types of distribution substation can be single, and then the number of chamber indicating the number of transformer needed. If 2 chambers type is using, it can be recognized by using 2 doors of the size of 2400 mm wide times 300 mm height. And then the types of transformer can be all immersed type, which is cheap but low efficiency for small users, or it can be cast resin type, which is dry, more expensive but have higher efficiency for large customer. The nominal volt ampere capacity of the transformer are usually in 300, 500, 750 and also 1000 kVA. Okay, we are talking about distribution substation just now, or simply call it as DS. So, what are inside the DS? So, inside the DS, we have switch gear, and then we have transformer, and then we have finally low voltage distribution board. Basically, the 400 volt supply will then connected to the kilowatt hour metering system through low voltage underground cables. So this kilowatt hour metering is usually at the user side. And then for the layout of an DS for single chamber can be like this. So we have one switch gear room, and then we have transformer room, and then lastly we have low voltage board. So this is where the outgoing points will be. Okay, this is the example of the single chamber distribution substation. The layout is like this. So we can see from the layout, there for the single chamber only one door is presented at the distribution substation. So how about the double chamber? So for double chamber, we have two doors. Here one, and then another one here. So the door is function as where the incoming and outgoing supply is connected. Now we move to the types of electrical supply users. So for higher voltage, so a higher institution, shopping complex, large factory are using high voltage, and then for low voltage is for the domestic users, shop lots and public. Okay, now we move to the low voltage distribution network. Okay, now we go to the low voltage electrical supply. So what is the types of low voltage electrical supply? So it can be two types, which is 3-phase 4 wires. It represents for 400 volt. Meanwhile, we have 1-phase 2 wires represent for 230 volt. And then types of low voltage electrical installation can be for small industry building, small commercial buildings such as shop, office, restaurant, small building, residential building like condo, terrace, apartment, and then small public building like wet market, bus station, and also for public utilities such as street light, traffic light, and etc. And then what is the main component in a low voltage electrical supply distribution system, especially for building? So we need kilowatt hour meter from TNB, we need main switchboard MSB, we need also sub switchboard SSB, and also distribution board DB. So this is the example of a residential connection. So this is the distribution substation, and then this is the meter, and then this is the load. So from the distribution substation to the meter is from the TNB, and then loads is from the customer. Okay, this is the example of industry connection. So from the main switching switch, so into the factory, and then go to the distribution substation, and then from the main here, so we go to the SSB. So this is the example of the industry connection. Okay, this is the example of a main switchboard that we have in the industry, and then this is the example of sub switchboard SSB that we have in the industry. Okay, this is the low voltage electrical supply, for example for double story house. So we can see here from the incoming TNB, we go through the kilowatt hour meter TNB, and then from the kilowatt hour TNB we go to the first distribution board at the ground floor. So from the distribution board we connected to the lighting and also power. And then at the first floor, we have second distribution board, and then also connecting to the lighting and power. So in the real life, we can say not only connected to the lighting and okay, this is the example for low voltage electrical supply for terrace house installation. So the kilowatt hour meter is at the outside the house itself. Alright. Okay. This is the power triangle or power diagram that you need to understand, and will be used to calculate our bill later on. Okay, now we move to the load characteristic and tariff rate. So, under the load characteristic and tariff rate, we need to consider some economic aspects. So, A utility company must plan for the electricity demand in advance as requested by its consumers. So, some common terms used are connected load, maximum demand, demand factor, average demand, load factor, and also coincident factor. So, the connected load is the sum of the rated maximum value of all loads used by consumer. It may be expressed in watts, kilowatt hour, ampere, horsepower, kVA, etc. And then the maximum demand is the highest or peak demand for a specified time. So it might be in hour, day, month, or year. So demand factor, in short DF, is the maximum demand divided by the connected load. And then the average demand is the sum of the total load in kilowatt hour divided by the load period hour. The load factor is the average demand over the maximum demand. Load factor is always less than 1. So, this is how to calculate the load factor, which is average load in kilowatt hour divided by maximum demand times demand period. And then also can be used average demand in kilowatt divided by maximum demand. And finally, the coincident factor is the maximum demand of a system or okay. This is the group of coincident factor from ESA TNB. So we can see here the coincident factor for residential, commercial, industrial, and etc. So ESA is the Electricity Supply Application Handbook. Okay, now we go to the example 1, economic aspect. Okay, a load rise from 0 to 10 kilowatt instantaneously and stays constant for 1 minute, then rise to 20 kilowatt and remains constant for 1 minute. Continue at this rate of rise until it reaches the maximum value of 50 kilowatt for 1 minute, then instantly fall to 0 for 1 minute, after which is again a rise in 10 kilowatt steps at 1 minute interval to a maximum of 50 kilowatt and returns to 0 for 1 minute. If the load continues to vary in these steps, what is the average demand over the first 15 minutes, and then over the second 15 minutes, and also over the 30 minutes demand intervals? We need to draw the load rise. So it said that a load rise from 0 to 10 kilowatt hour instantly stays for 1 minute. So this is 10 kilowatt hour, and then this is 1 minute, and then rise to the 20 kilowatt hour, also stay for 1 minute, continue this rate of rise until 50. So this is 50 kilowatt, and then instantly falls to 0 for 1 minute. So falls to 0 here. So this pattern is continue. So for the first, so we can calculate from this graph, we can calculate the demand for 15 minutes. So okay, now we can answer the question number 1. What is the average demand over the first 15 minutes? So to calculate the average demand over the first 15 minutes, we need to know the total demand. So the total demand over the first minutes can be calculated by calculate the area under the graph. here. So from the graph, we can say that we have 10 kilowatt hours times 3 times here, and then 20 kilowatt hour and also 30 kilowatt hour we have 3 times under the area under the graph. Only 2 times for 40 kilowatt hour and 50 kilowatt hours, so that we can calculate the total demand by 10 kilowatt hour times 3 plus 20 kilowatt hour times 3 plus 30 kilowatt hour times 3 plus 40 kilowatt hour times 2 plus 50 kilowatt hour times 2. So we calculated, we got it as 360 kilowatt. And then the average demand over 50 minutes can be calculated by total demand divided by the period hour. So 360 kilowatt divided by 15 minutes, we got 24 kilowatt hours. Then how about over the second 15 minutes? So to calculate the total demand for the second 15 minutes, we need to draw this graph again and again until we get another 15 minutes. And then when we draw and calculate it, we have 390 kilowatts. Thus, the average demand is 390 kilowatts divided by 15 minutes, we have 26 kilowatt. And then, so for the over the 30 minutes demand interval, we need to calculate the demand over 30 minutes. So the demand over 30 minutes is 360 kilowatt plus 319 kilowatts. So we got it as 750 kilowatts. So the average demand over the 30 minutes demand interval is 750 divided by 30 minutes, we have 20. We move to the second example under the economic aspect. So we read the question first. A factory consumes 425 kVAh in a year with the yearly average power factor 0.86. If the maximum demand was 120 kilowatt, find the average demand, annual load factor, and also if the factory decided to increase the electricity usage to 450,000 kilowatt hour and the load factor to 65%, what will be the maximum demand? Okay, now we can calculate the average demand. So the average demand is the sum of total load in kilowatt hour divided by the load period in hour. So the sum of total load is 425 times the power factor 0.86 divided by 365 times 24 hours. So we got the answer 41.74 kilowatt hour. And then for the load factor is the average demand in kilowatt divided by maximum demand. So we know that the average demand in kilowatt is 41.74, and then the maximum demand is 120 kilowatt, got from the question. So we divided, we got it, the answer is 35%. And then finally, if the factory decided to increase the electricity usage to 450,000 kilowatt hour, the load factor to 65%, what will be the maximum demand? So 450 kilowatt hour divided by the 876 hour times 0.65 the load factor. So the answer will be 79.03 kilowatt hour. So 876 is 300. Okay, we move to the example 3. So we have a low cost flat consists of 12 North Florence lamp with 40 watts, for NOS ceiling fans with 60 watts, for NOS 13 amp socket outlets, and then we need to determine the total connected load, the demand factor, the maximum demand, the total maximum demand, and also coincident factor. Okay, this is your homework to be submitted as your proof of attendance. Okay, now we move to the tariff. So, tariff is the rate of charging for electrical energy supplied by the utility company to its consumer. Tariff charge depends on the various factors such as types of consumer, types of service, total fixed running annual charges of the utility company, and also facility for calculating the bill. Definition of electricity tariff is the total actual charges, fixed plus running, divided by total energy supplied to the consumer. Three types. Okay, now we move to the TNB tariff. So, we refer to the TNB tariff book updated 2011. Power factor tariff is the low power factor penalty. Okay, it can be divided into two. The first one is below 0.85 and up to 0.75 lagging. Another one is below 0.75 lagging. Okay, when your power factor is in this range, the penalty will be added to your bill. So, for the below 0.85 and up to 0.75 lagging, 1.5% of the bill for month for each 100 will be charged. Meanwhile, when your power factor is below than 0.75 lagging, a supplementary charge of 3% of the bill for that month for each 100 will be charged. Okay, example 4, the power factor tariff. So, read the question. A medium voltage industrial consumer having the following data for its monthly electricity bill. The total electricity consumption in kWh is 160,000 units. The reactive power consumption in kVAh is 120,000 units. The monthly load factor is at 68%. For each kilowatt of maximum demand per month is Rm 25.30 cents per kilowatt, and for all kilowatt hour is 28.8 cents per kilowatt hour. So determine the monthly maximum demand for this consumer, takes 30 days per month, and then what is the total monthly bill charge for this consumer, and recalculated the total monthly bill charge if the reactive power consumption is increased to 150. Okay, now we calculate the monthly maximum demand. So the monthly maximum demand can be calculated by 160,000 kWh divided by 0.68 times 30 times 24 hours. So we got 326.8 kilowatt, and then we calculate the monthly bill without power factor consideration, and then we got that 326.8 kilowatt hour, which is monthly maximum demand, times the rate of the maximum demand for each kilowatt hours, 25.3, plus the total electricity consumption in kilowatt hours, 160,000 kilowatt hours, times the for all kilowatt hour rates, which is 28.8 cents. Okay, so we got the total bill without power factor consideration is Rm 54,348.4 cents. And then using the power triangles, we got a new power factor is tangent the reactive power divided by the kilowatt hour, and then we got 0.8. So we have the poor power factor charge, so the power factor is 0.8, so we need to charge 1.5%. So times the 0.85 minus 0.8 times 100 times the bill, and then we got the charge is 4,076.10 cents. So the total monthly bill charge is 54,348.4 cents plus the penalty of Rm 4,076.10 cents. We got it. This is the final bill to be. Okay, how about question number 3? Recalculate the total monthly bill charge if the reactive power consumption is increased to 150,000 units. So, this is your homework to be submitted as your proof of attendance. Okay, see you again. Assalamualaikum warahmatullahi wabarakatuh.